Hi, I'm James Rango, editor of Interference Technology. Welcome to Day 2 of EMC Live Fundamentals 2021. I hope everybody enjoyed Day 1 of the full day of product demonstrations and technical webinars. Our first session is What's with the Number? Decrypting the Math of EMC. This will be presented by Dean Landers, Supervisor of Application Engineering at AR/RF Microwave Instrumentation. Dean is the Supervisor of Application Engineering. He's actively engaged in the new application and product development, system development and integration, customer support, and training with hardware demonstrations for both customers and company personnel. In this presentation, he will help viewers understand where the equations come from, understand quick unit conversions, and help viewers understand how a decibel is always a decibel. I encourage everyone to ask questions, and Dean will get to answer as many as he can at the end of the session. Without wasting any more time, Dean, please take it away.
Hello and welcome to another edition of EMC Live. Thank you for the introduction, and today we're going to be talking about the math of EMC. And whether you are an engineer, a technician, a manager, or a customer in an EMC laboratory test environment, the math can sometimes look like a different language. And my experience is that people walk into a laboratory environment and look at some of the numbers and don't quite understand what they're looking at. So, the goal of this presentation is to kind of introduce the math of EMC to those who've never seen it before, to go through some of the basics about the conversions and where things come from, and to kind of roundabout way give a basic understanding of what we're talking about when we talk in the terms that we've discussed in EMC. So, with that, the first thing that we'll hit up is Ohm's law and impedance. Talk about why we use decibels in this environment, in these measurements. Talk about how to convert between logarithmic and linear terms. We will talk about how to convert between dB microamps, dBm, and dB microvolts. We'll hit up on decades and octaves. We'll touch on how a dB is a dB no matter how you slice it. So if you have a dB in power, what does that dB do in field? And then we'll give us some anecdotal evidence about things that I saw in the test laboratory where a customer was having an issue and wanted us to do something. And with regards to subtracting ambient noise from their measurement to show that they passed, and how that quite didn't work. So, as a little precursor to this, we're going to assume that everybody viewing this or listening in has a working knowledge of basic math. You know Ohm's law, and you know how exponential numbers work. So with that, let's get started. The first thing that we're going to talk about is Ohm's law and impedance. And we should all know Ohm's law is a fundamental law in electrical engineering and physics, for that matter. With Ohm's law, we can derive power and watts, voltage and volts, current in amperes, and resistance or impedance in ohms. And in our environment, in the EMC environment, Ohm's law is king. So we all know that power is voltage times current, and voltage is current times impedance. So with that, we always know how to get from one to the other, right? We always know how to get from, if we have our current, we know how to get our voltage, and if we know our voltage, we know how to get how much power we have. And the reason for that is that our nominal impedance in EMC testing, in RF, is almost always 50 ohms. So since we know that we're always going to be working inside of 50 ohms or a 50 ohm system, we only need to know algebra at that point, and from there we can get any of the above 4 values. If we know that the impedance is 50 ohms, we know how we can get our power, we know how we can get our voltage, and we know how we can get our current. So Ohm's law with our impedance is the very beginning of where the math starts in EMC. And it's basic electrical engineering. Circuits 1, if you went to school for it, you know that Ohm's law is basically the things they teach you on the first day. So you're probably asking, why do we use 50 ohms? You could be working in EMC for 20 years and not know why 50 ohms is kind of the golden impedance for our industry. And what it comes down to is losses and power. So if you look at a transmission line loss versus characteristic impedance, you'll see that insertion loss is a minimum at around 77 ohms. And if we look at maximum power transfer versus characteristic impedance, we get a maximum power at around 30 ohms. So if you take the middle number of that relationship between 30 and 77, which is, take the average, 107, be 53.5, people decided that 50 ohms was kind of chosen as being in the middle of that relationship between losses and power. So transmission line loss versus characteristic impedance being 77 ohms, and then in maximum power transfer versus characteristic impedance, we get a maximum power drive at around 30 ohms. So they took the average, made it a nice round 50, and ever since then, things have been using 50 ohms. You do see some 100 ohm systems out there with some of the European BCI constructs and things like that, but it all starts at 50. Everything starts at 50 ohms, so we use 50 the whole time. And this does assume that there's a short run of cable or transmission line. If you have a long transmission line, your impedances are going to go up, and if it's very, very, very short, your impedance may not be quite up to 50. So we're going to assume a short run of cable or transmission line. We've talked about Ohm's law, we've talked about 50 ohm impedance. Now we're ready to actually discuss the math of EMC. And where we start is we start at the decibel. EMC testing almost always uses the decibel, or dB, to express our units of measurement. And the reason for that is we need a logarithmic notation. You might ask, why do we need a logarithmic notation? Well, decibels are using the dB as a way to express the numbers that are increasing very quickly or exponentially as they relate to what's happening in an EMC system. So if we are looking at power, 1 watt is 30 dBm and 10 watts is 40 dBm. So we went from 1 watt to 10 watts in a matter of 10 dBm. However, if we add 20 dBm to that, we've increased it to 1 kilowatt. So in our measurements in this industry, EMC results are often very large numbers or very, very small numbers. So in the immunity world, we're usually hitting very large numbers. We're using kilowatts of power, or at least on terms of hundreds of watts of power. And in the emissions world, we're using microamps or microvolts or milliwatts. So we need a way to express those numbers in the same fashion together on the same graphs and still have it all make sense. So that's what the dB does for us. So the dB gives us an easy way to relate the very small to the very large, and we can see it all together on the same graph. And also, when you're expressing in terms of limits, like an emissions limit, and you have an emissions limit that goes from 10 kilohertz to 18 gigahertz, that's a very wide range of frequency. However, if you express it logarithmically, you can show it on one piece of paper. You can show it on one graph. So the dB becomes a very powerful tool in our business, in our industry, so that's why it's used. So we understand why we use decibels. Now we need to know how to convert between some of our decibel numbers. And it's very simple. Converting between linear numbers, so power, voltage, current, to logarithmic numbers. dBm or dBmW, dBm is short for dBmW. dB microvolts and dB microamps is very simple. And if you're the first time walking into a laboratory, the most numbers that you're going to see are dBm, dB microvolts, and dB microamps. There's only 3 equations that you really need to know. To get from power to dBm, it's 10 times the log of the power in milliwatts. So if you have a kilowatt, you need to convert that to milliwatts first. So if you have 1,000 watts, you have 1,000,000 milliwatts. Okay. Voltage is 20 times the log of voltage in microvolts, and current is 20 times the log of current in microamps. Interesting side note, if anytime you're talking about dB microamps, dB microvolts, dB dB anything, you have to convert, when you're using your logarithmic equation, you have to convert it to, you got to convert it to the unit that you're converting to. So if you have dB volts, right, it's 20 times the log of the voltage in volts. But most of the time, in the laboratory environment, you will see dB microvolts, dB microamps, and dBm. And you also should remember that since we are in a 50 ohm system, we need to remember that the impedance of 50 ohms in logarithmic terms is dB ohms is 20 times the log of the impedance, which is 20 times the log of 50, and that comes out to being 33.979. And we round that up to an easy 34. Most of the time in our business, you'll notice that we use nice round numbers. Okay, so 33.979 is close enough to 34. So dB ohm is 34, and that can help you get to the conversions between going from power to dBm to dB microvolts to dB microamps. And we're going to talk about that too. Before we get into converting between the two, converting between two measurements, so dBm to dB microvolts, there are things that you need to remember about dealing with logarithms. And the first thing we need to know is that adding in logarithm, or adding in dB, is the same as multiplying in linear terms. So if we have 13 dB microvolts and we want to add 44 dB microvolts, it gives us 57 dB microvolts. If we convert the dB microvolts back to linear and convert to microvolts, the reverse from the logarithmic expression is 10 raised to the dB microvolts over 20. So we have our microvolts is 10 raised to the 13 over 20, which is 4.47 microvolts. And then on the other side of the number, we have 10 raised to the 44 over 20 is 158.49 microvolts. If we know that what we're looking for here is that adding in logarithm is the same as multiplying in linear, if we multiply 158.49 times 4.47, we get 708.45 microvolts. If we want to convert that back to logarithmic terms, convert that back to dB microvolts, take 20 times the log of 708.45, we get 57.01. So that proves to you that adding in logarithms is the same as multiplying in linear. And conversely, subtracting in logarithms is the same as dividing in linear. So as a quick practice, you could take this and take 57 minus 44, giving you 13, and work back through the linear terms. dB1 minus dB2 is measurement 1 over measurement 2. You should get the same numbers. So that is something that you need to remember, that you can't just subtract dB from dB to get a linear number. You have to convert it to linear first, and then you have division or multiplication or whatever your application is. So something very important to remember when working inside the dB. We know how to convert the linear numbers to dB. How do we convert between dB microamps to dBm to dB microvolts in a 50 ohm system? It's very important to remember that we're in a 50 ohm system. Now, you're going to see this a lot in some of the measurements, especially on Spectrum Analyzer. Usually, Spectrum Analyzer is in dBm. Usually by default, I think they're in dBm. But some of your measurements are going to be dB microvolts. So be careful when you're taking a measurement off of a Spectrum Analyzer that you're not converting, or you're not double converting to dB microvolts. Sometimes, most of the time, I like to do that little conversion by hand. Get my number in dBm, add my factors in, and then convert to dB microvolts. Anyway, our impedance is still 50 ohms, so our conversion is 34. So if we want to convert dBm to dB microvolts, or dB microvolts to dB microamps, or dBm to dB microamps, whatever, here's how we do it. dBm is the measurement in dB microvolts minus 107. And dB microvolts is dBm plus 107. So if you have a measurement in dBm and you need to convert it to dB microvolts, you have to add 107 to it. Easiest way for me to remember that is that in our measurements, dB microvolts is always typically much higher than dBm, just in numbers. So if I have 0 dBm, I have 107 dB microvolts. Okay. If I have 13 dBm, I have 120 dB microvolts. dB microvolts is dB microamps plus 34. That's Ohm's law, right? So D equals IR. So our current times impedance, and remember that adding in dB is the same as multiplying in linear. Our impedance is 34. We're going to add that to our dB microamps, and that's going to give us dB microvolt. Same thing with current. dB microamps is dB microvolts minus 34. It's just a division at that point, right? dBm is dB microamps plus 73. And dB microamps is dBm minus 73. Okay? And if you look, 107 and 73 are 34 apart. And so that's kind of an indicator of how that all works. So as a little proof here, let's convert 0 dBm to dB microvolts. Okay, 0 dBm is what? X dB microvolts. 0 dBm is 0.001 watts or 1 milliwatt. And so applying Ohm's law, 0.001 watts is volts squared over 50 ohms. 50 ohms, 0.001 watts times 50 ohms, we use a little bit of algebra, is our volts squared. The square root of 0.001 watts times 50 ohms is how many volts? And that's 0.224 volts. So we take 20 times the log of 0.224 times 10 to the 6th. Remember, we're converting from we're converting to dB microvolts. We've got to make sure that our volts are in microvolts, and that conversion is times 10 to the 6th, and we get 106.987, which we round that to 107. So anytime you have dBm, you want to convert to dB microvolts, add 107. So that's how you do it. Okay, so we're going to move on a little bit from our dB world. I hope that we now have a basic understanding of how that math works. We're going to talk about some decades in octaves now. And kind of quickly, these are typically used in frequency ranges, and an octave is defined as a doubling or a halving of a value. So if our frequency is at 1 gigahertz, an increase of 1 octave is 2 gigahertz, octave above that is 4 gigahertz, an octave above that is 8 gigahertz, and 16 gigahertz, 32. And anybody who's a computer programmer out there, or a computer scientist, or a computer engineer knows that we work in powers of 2. So those numbers kind of probably seem familiar for you. Regarding octaves, if we're talking about this becomes very important in antenna design. You'll notice that in the design of high gain horns, or if you're designing any kind of EMC system and you need to use high gain horns specifically, a lot of times high gain horns are in octaves. So you'll have a 1 to 2 gigahertz high gain horn, a 2 to 4 high gain horn, a 4 to 8, 8 to 16, sometimes it goes 8 to 12, and then 12 to 18. So that's something that you'll see in the real world as you're, maybe shopping or pricing out things, or as we just searching for an antenna. A lot of times those are based on octaves. A decade, on the other hand, is defined as 10 times or a tenth of any value. So if we're at 1 gigahertz, an increase of 1 decade is 10 gig, a decade above that is 100 gig, and so on. So with that, if you're in the dB world, also decades are very important, especially in power. A decade above 1 watt, 30 dBm is 1 watt. Decade above that's 40 dBm, so we've added 10, but we multiplied 10, so that's 10 watts. Decade above that is 50 dBm. Decade above that is 60 dBm, and the power just goes 10 times, 10 times, 10 times. Okay, so when you're talking in dB of power, those numbers get very large very quickly. Limits will sometimes be expressed in terms of decades. For example, an emissions limit might be expressed as starting at 10 kilohertz and increasing 10 dB per decade to 1 gigahertz. So as we go up a decade, we increase 10 dB per decade, all the way up to 1 gigahertz, and that you'll see a nice slanted line. That's kind of a quick rundown of decades and octaves. One of the advantages of using decibels is that using decibels creates a situation where all units are relatable. So dB is basically a dB. So to increase an octave in voltage or field level, you need to add 6 dB. And to increase an octave in power, or double the power, you have to add 3 dB. So the interesting thing here is if we need to increase our field level from 100 volts per meter to 200 volts per meter, we have to add 6 dB to the field. That also means that we have to increase our power by 6 dB, not 3. For example, let's say we need 150 watts or 51.76 dBm to reach 100 volts per meter. And it's just a kind of an assumption today. And that means that 100 volts per meter is 163.2 dB microvolts per meter in this system. So since we're adding 6 dB to the field, we have to add, we need 169.52 dB microvolts per meter. And adding 6 dB to the power means we need 57.76 dBm. From what we've learned today, we have the equation here, and that shows that we need 600 watts. To go 6 dB in field, we have to increase the power by about 4 times. And from what we've learned today, I'd like to share a little bit of anecdotal evidence as to why this information is important. So when I was in the test lab, I ran a lot of military test programs. I did some of the testing. I oversaw some of the testing, and had a situation where a customer was failing CE 101 out of Mil Standard 461F, and this gentleman requested us to subtract the ambient noise from the measurement. If you don't know, when you fail a test or sometimes come within 6 dB of the limit, you typically run an ambient to show that all your measurement equipment and all of your factors and everything are within 6 dB or less than 6 dB away from the limit. So we agreed, but we reminded him that the actual subtracting of the dB microamp levels was inappropriate, and we had to convert everything to linear first. So we had 2 graphs on the display, one showing his measurement and the other showing the ambient. So the limit level was like 100 dB microamps in CE 101, and the measurement was about, I think, like 103.5, and the noise floor measurement was around, it's in somewhere in the 70s. So take, for example, 73 dB microamps. So if we convert the measurement of 103.5 dB microamps, we get 149,000 microamps. And if we convert the ambient level, we get about 4,400 microamps. So we subtract the two, we get 145,156.72 microamps, and we take 20 times the log of that, and we get 103.24 dB microamps. So he didn't really save himself much, and he was still 3 dB above the limit. So that goes to show you that knowing the math, knowing how to apply it, will yield positive results for you, knowing what you're doing in the test laboratory and showing it in front of a customer. So that's always a good example that I refer back to, something that I actually saw in the real world. So once again, I'd like to thank you for attending today. We'll open everything up for questions. And once again, I appreciate your time and hope to speak with you again soon.
Hey, thanks, Dean. Great presentation. Really appreciate your time. I want to thank everybody who attended this session and everybody who's attended EMC Live 2021 Fundamentals. With that being said, Dean, if you're ready, I'm just going to get right into the Q&A.
Okay, go for it.
All right, first question. How do equipment factors, antenna, cable, etc., play into converting the measurements?
Depending on what the conversion factor is, if it's cable, it's expressed in would be loss. If it's an antenna or a current probe or some other transducer, it's converting one measurement to another. So a current probe is converting current to a voltage output. Antenna is converting a voltage reading to a voltage output, which is then expressed in dB microvolts per meter or microvolts per meter. So it depends on the type of device that you have. But what they do is they create the end result of the measurement.
Okay, great. Next question. Just bear with me for 1 second. Should my spectrum analyzer be set to decibel microamps, decibel milliwatts, or decibel microvolts?
It depends on the type of measurement that you're making. However, be very careful about using a dB microamp measurement, because that will go ahead and create the factor of plus or minus 34 from your actual measurement. So when you're making measurements, you want your spectrum analyzer to typically be in dB microvolts, especially if you're doing emissions type measurements. The limits are usually expressed in dB microvolts, and everything in a line is dB microvolts. If you're doing a current measurement with a current probe, the factor of the current probe changes the amount of the measured current going through the current probe at that particular frequency to a voltage output. So then your end result at the spectrum analyzer should be in dB microvolts, because the current probe changes the current measurement to a voltage measurement. So instead of the plus or minus 34 at the current probe, that's basically an impedance transformer, right? So it's a change in impedance at the frequency. So in short, dB microvolts.
Okay, great. Next question. Should I use a power meter in watts or in dB milliwatts?
I always prefer to keep everything in dB and not convert to the linear term unless you absolutely 100% have to. The reason for that is, as you can see in some of the calculations that I showed during the presentation, it's not exactly 107, it's not exactly 34, it's 106.99, it's 33.97. If you start converting in between dB and linear, or logarithmic and linear, you run the risk of rounding errors factoring into your measurement or your resulting measurement. And if somebody is close to the limit in microvolts or dB microvolts, and you've converted a couple different times down the line, you run the risk of, albeit a small risk, you run the risk of changing the compliance decision based on rounding errors. You have to be very, very careful about that. Easiest way to prevent that is to keep the units all the same during the measurement. And then
okay,
convert
great.
it in if
And,
you have to.
awesome. And final question. How do I interpolate dB as opposed to linear measurements or limits?
It depends on how, if you have a log-log graph, if you have a logarithmic linear or a semi-log graph, the interpolation can be different. So sometimes you have to convert to actual linear and interpolate. What I'll do is when we answer the questions off of the to the audience, I will show the actual calculation, because to explain it here may be a bit difficult.
Okay, great. Well, any questions that were asked and not answered, as Dean just mentioned, they will be answered and posted online after the fact. Dean and AR, once again, I just want to thank you for your technical session. I also want to thank everybody who's attended and encourage everybody to attend the rest of day 2 of EMC Live Fundamentals 2021. We look forward to seeing you at the next session, and thanks for your time. Dean, have a good one.
Thanks, everyone.